Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. We are back with our next lecture 3.8 about single crystal X-ray diffraction techniques, in which firstly we have studied the single crystal X-ray diffraction technique, in which the source used was X-ray beam, and after that we have studied another diffraction technique, that was neutron diffraction technique, in which neutron beam was used, and we have also discussed the comparison and advantages and disadvantages of the neutron diffraction technique. And after that we have started the electron diffraction technique, in which electron beam is being used to study the crystal structures. So this lecture is also the continuation of the previous lecture, in which we have started the electron diffraction technique, and we have studied its basic, and also we have studied the principle of the electron diffraction technique, and we were discussing the advantages and disadvantages of electron diffraction technique. Here we will continue that uh, disadvantages. In spite of these disadvantages, electron diffraction is very useful and complements the various X-ray techniques. Thus, with X-ray, the scattering efficiency is small. Secondary diffraction is rarely a problem, and intensities are reliable, but relatively large samples are needed. Whereas with the electron diffraction technique, the scattering efficiency is high and intensities are unreliable, but very small sample can be studied by using this electron diffraction technique. This technique is very useful for obtaining unit cell and space group information for crystal smaller than 0.1 to 0.2 millimeter in their lateral dimension. It is in fact the only reliable method for obtaining such information, since it gives a direct picture in 3D. In reality, the picture are 2D sections through 3D space of the direction of diffracted beams. From such information, the diffracted beams can be assigned HKL, that are Miller indices, and the unit cell can be determined. From the pattern of the systematic absence, further information on the lattice type and space symmetry, leading to determination of the space group, can also be obtained by using this electron diffraction technique. And in the absence of the direct unit cell and space group information, powder XRD pattern may be indexed using various trial and error procedures, but there can be uncertainty in the result obtained, especially in case where a superstructure may be present that show up only weakly in the powder XRD pattern. In spite of its utility, electron diffraction is underused in solid-state chemistry for unit cell and space group determination. probably because it is time consuming and requires a high level of expertise for data interpretation. So it is, however, of limited use for full structure determination, but of the unreliability of diffraction intensities. The electron diffraction is unsuitable as a routine method of phase identification in relatively large samples and samples more than 10 milligram or more because of the sampling issue. The technique focuses on individual grains on at a time. This technique focuses on individual grains once at a time rather than giving an overall average analysis of the sample. It is useful, however, in some areas when very small quantities are available, and it is also useful for thin film samples. It also useful for detecting small amount of impurities phases, and it is also useful in all these cases. There would be insufficient material to show up in XRD analysis. Here are the basics of electron diffraction. In electron diffraction, no absorption occur, no thermal vibration are created, there are no multiple scattering, there is large object macroscopic single crystal study, and the distance between the crystal and film is greater than the wavelength of electron. And the electron interaction with matter is really unlike other type of radiation used in diffraction studies of material, such as X-rays and neutrons. Electrons are charged particles and interact with matter through the Coulombic force. This means that the incident electrons feel the influence of both the positively charged atomic nuclei and the surrounding electrons. And in comparison with X-rays, X-rays interact with the spatial distribution of the valence electron, while neutrons are scattered by the atomic nuclei through the strong nuclear force. In addition to this, the magnetic moment of the neutron is non-zero, and they are therefore also scattered by magnetic fields. Because of these different forms of interaction, the three types of radiations are suitable for different studies. While discussing about the intensity of the diffracted beam using electron beam, an incident beam of the electron is scattered by the atoms of a crystal unit cell. Since the atoms are equally spaced, are spatially distributed in the unit cell, so there will be a difference in phase. And the scattering power of an element depends on the type of radiation considered, because electrons interact with the matter through different processes. Bragg equation, which is the most basic equation in the crystallography, the measurement principle of electron diffraction is based on this equation. Bragg's diffraction occurs when electromagnetic radiations or subatomic particles waves with wavelength comparable to atomic spacing are incident upon a crystalline samples, and they are scattered by the atoms in the system and undergo constructive interference. For a crystalline solid, the waves are scattered from lattice planes separated by the interplanar distance d. The scattered waves interfere constructively and they remain in a phase since the path length of each wave is equal to an integral multiple of the wavelength. The path difference between the two waves undergoing constructive interference is given by 2d sine theta, where theta is the scattering angle. This leads to Bragg's law, which describes the condition for the constructive interference from successive crystallographic planes of the crystalline lattice. 2d sine theta is equal to n lambda, where n is an integer determined by the order given and lambda is the wavelength. Here is the pictorial elucidation of the Bragg's equation in which two different waves are coming and striking the different planes, and the wave that is striking the plane under the first plane is traveling a distance greater than the distance of the upper wave, and this distance is equal to 2d, and we can get this distance by the wavelength difference. That means this the second wave can travel the distance that will be equal to one wavelength, two wavelength or three wavelength depending on the spacing between the two layers. So this 2d sine theta will be equal to n lambda, that is the difference traveled by the second wave may be greater than one wavelength or it may be greater than 2, 3, 4 or any integral value which is depends on the difference between the spacing of the planes of the atoms present in the crystal. So discussing about the instrumentation of the electron diffraction technique. An electron diffraction tube consisting of electron gun. It also carries carbon target and a luminescent screen. These are the basic elements that are present in the electron diffraction instrument, and it is used for this experiment. With this special vacuum tube, electrons are produced and accelerated, and their diffraction on the carbon layer can be studied. That carbon layer may be polycrystalline layer. Electron gun. The heated cathode and anode make up the electron gun, and then the electrons are produced by heating the filament that is located inside the oxide coated that can metal can and that can be called as cathode. Electrons are ejected by thermionic emissions from this heated piece of metal. Once emitted, the electrons are accelerated by two pairs of anode rings with adjustable acceleration potential. The voltage that the required is 2000 to 5000 volts. Kilowatt power supply between the cathode and anode and form an electron beam. Each electron in the beam has a kinetic energy equal to the accelerating electronic and the electron's charge. What is carbon target? As the electron beam passes through the anode, it meets the very thin mesh containing vaporized graphite carbon. The carbon suspension acts as a polycrystal, and the diffraction caused by the mesh can be neglected. Here is a pictorial diagram in which electron gun is shown on the left, which produces electron beam that strike the sample at certain angle, and after striking the sample, this beam can be scattered at different angles because of the planes present in the sample, and then this scattering that are known as diffraction pattern can be recorded as on the film or can be recorded by the detector. Luminescent screen. Leaving the target, diffracted electrons travel a certain distance L and strike a phosphorus screen. That phosphorus screen is also known as luminescent screen. The beam now appear as a concentric rings around a bright center. This pattern can be visualized as a set of one-dimensional diffraction pattern of bright spots rotated about the axis of the electron beam. Here is electron diffraction experimental diagram in which we can see that electron beams are produced by applying high voltage, and then these electron beams are strike over the sample, and after that these are recorded in the form of diffraction pattern. Transmission electron microscopy. This is also known as TEM. Transmission electron microscopy TEM, also sometimes conventional transmission electron microscopy, that is CTEM, is a microscopy technique in which the beam of electron is transmitted through the specimen to form an image. The specimen is most often an ultra-thin section less than 100 nanometer thick or a suspension of grid. An image is formed from the interaction of the electron with the samples, and as the beam is transmitted through the specimen, the image then magnified and focused on an imaging device such as a fluorescent screen, a layer of photographic film, or a sensor such as the charge-coupled devices. In transmission electron microscope, a thin specimen is irradiated with an electron beam of uniform current density. An electron illuminates the specimen through the condenser lens. The electron intensity distribution is magnified with the lens system and viewed on a fluorescent screen. The image can be recorded by the image plate or digitally by the CCD camera. Design of the transmission of electron microscope. A simplified ray diagram of a TEM consists of transmission electron microscopy consists of electron source, condenser lens with aperture, specimen, objective lens with the aperture, projector lens, and fluorescent screen. These can be seen on right side of the screen, in which transmission electron microscope can be studied graphically or in the form of picture, where electron source comes first and then condenser lens, and after that the specimen is present. Dear student, now we are going to start our next topic about electron spectroscopy diffraction technique, and this is SEM, scanning electron microscopy. In scanning electron microscopy, SEM, it has become a powerful and versatile tool for material characterization. This is especially so in recent years due to the continuous shrinking of the dimension of material used in various applications. The scanning electron microscopy scan a focused electron beam over a surface to create an image. The electron in the beam interact with the sample, producing various signals that can be used to obtain information about the surface topography and composition. So here we are going to look that why we use electron instead of light in a microscope. Given sufficient light, the human eye can distinguish 2.2 nanometer apart without the aid of an additional lens. So this distance is called the resolving power or resolution of the eye. A lens or an assembly of lens and a microscope can be used to magnify this distance and enable the eye to see points where closer together than 0.2 millimeter. So a modern light microscope has a maximum magnification power of about 100 times greater than this power. The resolving power of microscope was not only limited by the number of quality of the lens, but also by the wavelength of the light used for illumination. White light has wavelength from 400 to 700 nanometers, The average wavelength is 550 nanometer, which result in the theoretical limit of the resolution of the light microscope in white light of about 200 to 250 nanometer. The figure below shows 2 points at the limits of detection, and the two individual spots can still be distinguished. Electrons have much shorter wavelength, enabling better resolution. The 2 points showing the limiting of detection in the figure can be seen. Dear student, this was some basic thing about the scanning electron microscopy, and in our next lecture we will discuss that how scanning electron microscope works and what are the main components that are used in scanning electron microscopy.